Okay, so we are now live. I'd like to start very briefly just saying that the Topos Institute is really happy to host this seminar, and I'm going to pass over to Martin Hyland for more.
Okay, so welcome to MCAT's for Emerging Category Theorists, a seminar run by the Topos Institute. So its down-to-earth aim is to give young researchers the opportunity to speak about their work to category theorists scattered as we are across the world. And this is where we will come in, to benefit from feedback from the wider community, that's us. So it's good to see that there are a decent number of people here already, and also from many time zones. But MCATS has also the perhaps more ambitious goal of helping the next generation of researchers, as it says in the blurb, become wonderful speakers. And I want to dwell on that for a moment. We live in a crudely utilitarian culture. And as a result, the fact that mathematics is so useful creates a strange kind of problem. It distracts us from the intrinsic values which lie in the subject itself. And the importance, especially for abstract mathematics, of being guided in our mathematics by what the mathematics tells us. If you take that on board seriously, then you see that giving a great talk is not deep down an issue of presentation. Rather, it involves us getting clear in our own heads about the essential mathematical content of what we've been thinking about, and then expressing it honestly and with as much simplicity as we can muster to our fellow mathematicians. Well, maybe that's a big ask for all of us, but it seems to me excellent that the Topos Institute, which after all is focused on applications-oriented category theory, is running MCATS, which expresses such very high ideals. So I think that's enough by way of introduction to MCATS. So before introducing the speaker, I'd just like to hand over to Eugenia Cheng, who will be monitoring the proceedings.
Thanks, and hello everyone, thanks for being here. I just wanted to say a word about how we're going to do questions. So if you would like to ask a question, please type it into the chat just to me. And so this is to encourage people who might be shy about the sorts of questions they want to ask. So it doesn't have to be something that everyone will see. Just type it to me, Eugenia Cheng, in the chat, and then I will convey the questions to the speaker. So nobody ever needs to know who posed the question. I personally am very shy about asking questions because I'm worried everyone will think that my question is stupid. And so this is how we're going to do it. And if you're confused, if you would like something clarified during the talk, then Jade will try to stop at the end of each section and ask if there are any clarifying questions, at which point I will look in the chat and pose any questions about that section, if in case there's something that needs clarifying then, and then anything else we'll do at the end. So you can put questions at any time you want, and I'll just defer the ones that are more general towards the end. That's it, thanks.
Okay, thank you, Eugenia. So now it's a great pleasure to introduce our first speaker in what I hope will be a long-running seminar series. So it's Jade Master, and the title is The Universal Property of the Algebraic Path Problem. So over to you, Jade.
Hi, thank you very much. So first of all, I'd like to thank everyone who organized this seminar, including Tim Hosgood and Brendan Fong, and especially Eugenia Cheng. She spent a lot of time with me working on this presentation, so know that a lot of her work went into this as well. Also, I'd like to thank everyone who helped me come up with the math for this talk. As lots of people know, math is created by communities and not individuals. And there was a large community which helped me figure this stuff out. So even though it only has my name, there's a lot of other people's work who is represented here. Okay, so first of all, I'm going to give a quick overview of what I'm going to talk about. Okay, so the basic idea is that I'll be talking about graphs. So graphs, and they're going to have weights on the edges. And those weights can represent lots of various different things. They can represent distances. But the main sort of category theory idea here is that this can represent the data of an enriched category. And the advantage of representing these graphs as enriched categories is that it allows us to generalize to lots of other situations. And also there are lots of really nice constructions on enriched categories that we can use. And I'll show you how this sort of gives a nice characterization of the algebraic path problem. And one other thing is that there's a lot of linear algebra in this talk, and that's on purpose because I think a lot of mathematicians take comfort in linear algebra. And I hope that's something that we can all use in these times. So hopefully it'll be category theory and linear algebra combined is the goal. So the table of contents. So first I'm going to talk about what the algebraic path problem is, and I'll go through some examples. Then I'm going to talk about free categories, and not enriched ones, just regular free categories, and how that sort of relates to the algebraic path problem. Then I'm going to talk about the enriched version of what I talked about before, so how you turn free categories into enriched categories. And then I'm going to talk about applications of that for compositionality and sort of how we can construct solutions from smaller solutions. So great, let's get into it. So first of all, the algebraic path problem is going to generalize the shortest path problem. And some people may be familiar with the shortest path problem, but it's not entirely obvious, definitely. So suppose you have a graph like this with these three vertices, A, B, and C. And the numbers on those edges represent the distances of traveling along that edge. So if you wanted to find the shortest path from A to B, there's two possible routes you could take, right? Either you could go directly from A to B, or you could go from A to C and then from C to B. But if you were to sort of add up the total distances along each path, well, this path takes 3.14 distance, and this path takes 52 plus 4 distance, so 56. Okay, so what calculation did we just do? Well, first of all, we looked at the paths that go from A to B. There's two relevant ones here. And then we found the lengths of those paths, and that's summarized in this table over on the right. And then to find the shortest one, what we did is we took all the lengths, put them in a set, and then took the minimum of those lengths. And in this case, that minimum is going to be 3.14. So in this calculation, we've really just used two things. We've used the minimum operation, and we've used the sum operation. So we're using min and plus. And these are two operations on real numbers that we've been using. So I guess the natural question is to ask, what structure allows us to generalize this computation, or what's a nice level of abstraction to encapsulate two operations like this? And the answer is semirings. So a semiring is like a ring, except the plus and the additive thing only is a monoid, and it doesn't need to have negatives. So the canonical example, at least from my point of view, or one that I've seen a lot, is the natural numbers. That's the usual plus and times. They form a summing ring. Note that it's not a ring because natural numbers don't have negatives. But the motivating example for this talk is going to be the positive real numbers, including infinity. So this example will be a semiring. And the additive monoid will be minimum, and the multiplicative monoid will be plus. So be really careful because this example is super confusing. So the multiplication is the usual plus, and so that's confusing to begin with. But if you think about what the neutral element should be for a minimum, well, it should be the biggest possible thing, right? Because if you take the minimum of something with infinity, that's always going to be the something. So it's weird because the additive identity is infinity, which is like the opposite of what it usually is. And the multiplicative identity is 0. So this semiring is sometimes talked about a lot in algebraic geometry. And it's called maybe the min plus semiring. But we'll see what it's used for in a moment. So there's this sort of correspondence between weighted graphs and matrices. So the idea is that if you have a matrix, you can draw a weighted graph. And what you do to draw that weighted graph is, first of all, the set that the matrix is on is going to be the vertices of your weighted graph. And then if an entry of the matrix, the ij entry has value x, then the weight of the edge between I and j will be x. And if the ij vertex has value equal to the additive identity, then there will be no edge drawn in the weighted graph. And if it's a weight between a vertex and itself, then we're just going to draw that node directly above the node. So as you can see on the graph to the right, there's a matrix down below the definition, which corresponds to that graph. So for example, you could go to this 2.7 part of the matrix and then go over to the graph. And so this is the second and third. So it's an edge between the second node and the third node. So what's the point of writing weighted graphs and matrices and corresponding them in this way? Well, the point is that now we can suddenly do matrix operations, and they will correspond to really fun and interesting things on those weighted graphs. Right, so finally, I'm going to talk about what the algebraic path problem is. So given a set X of vertices, and then also a matrix, so it's going to be from X times X to R, then an edge in your matrix, which is also sort of dually a weighted graph, is just a pair of vertices. So keep in mind that this sort of edge doesn't need to have a weight on it to be considered an edge. The weight could be infinity, and we wouldn't draw it in the graph, but it's still considered an edge, which is kind of weird. A path in your matrix is a sequence of composable edges. So, for example, it's a sequence of edges, and the target of the first edge must always match the source of the next edge. And if you want to take the weight of the path, what you do is you take the product of the weights of each edge, which is contained in that path. And keep in mind that for a motivating example, it's going to be the positive real numbers. And the product is actually going to be plus, which is one of the confusing things. So this weight is going to be a sum. Okay, so now finally, I can tell you what the algebraic path problem is. So let P sub ij be the set of paths starting in I and ending in j. Then, as we saw before in the previous slides, if we want to find the shortest path, we take the length of each path in Pij, and we take the minimum of all such lengths. And that will give the length of the shortest path. And the way that the algebraic path problem generalizes this is it turns the minimum into a sum. And it turns the weight into the weight of an arbitrary semiring, which will use the product of an arbitrary semiring. But keep in mind, for shortest path, that product is going to be the total length, which is sum again. So there's sort of confusing like switch of sum and weight. But if you work with this for long enough, you'll get used to it, but it is very confusing at first. So I guess bear with me. Okay, so that's the general statement of the algebraic path problem. And it turns out that lots of really nice examples can be phrased in this way. So here's another example. So we already saw the first example, which was shortest paths. It can be phrased in this way when you replace the sum with minimum. But if you take another semiring, let's call them the Booleans. I use Blackboard bold for them. The Booleans are the usual true and false with or and. And the or and, they work sort of how you would expect in terms of logic. So true or false is true, false and true is false. So it informs the semiring once you give them those operations. So it's considered this this weighted graph, this B-rated weighted graph, and it comes from a matrix. And that matrix will have a value of true if there's an edge drawn between two nodes, and it will have a value of false if there's no edge drawn. So in particular, the matrix for this graph here would be a 4x4 matrix because there's 4 nodes. And for example, the 1, 2 entry would have a value of true because there's an edge from A to B. Okay, so let's compute the algebraic path problem on this weighted graph. So first of all, we need to enumerate all the paths, or at least all the relevant paths. So first of all, there's a path from A to B, B to C, and then C to D. And there's another path from AC and then C to D. And then there's lots of other paths, which I am not going to write in this table because there's an infinite number of them. Really, you can go wherever you want. But the only path which is going to have a value of true is the one which goes AB, BC, and CD. Because remember, the weight of a path, what it does is it multiplies the weights of each edge. So the weights of multiplied together of this first edge that I've been talking about is going to be true and true and true, which is true. And then you go the other way, there's a false here from A to C, so it's false and true, which equals false. And all their paths are going to be false. Okay, so the algebraic path problem, it computes the sum over all such paths from A to D of the weight of those paths. In this case, the sum is going to be or, and the weights are, as we've enumerated above, are going to be true, and then the rest are false. So it's true or false or false or false, and so on, if you go into infinity. And true and false is always true. So the solution to the algebraic path problem in this case is equal to true. And this reflects the fact that A and D are connected. On the other hand, you can compute the algebraic path problem from D to A. And D to A are not connected. And you can see that because the weights of all the paths connecting them are equal to false. So when you OR them together, you're going to get false again. So the algebraic path problem, when you choose the semiring of Booleans, is it detects connectivity. And there are lots and lots of other examples. I was so impressed when I first heard about the algebraic path problem because it really touches so many subjects. So we already talked about this first example here with 0 infinity, that gives shortest paths. If you sort of change the operations around with the sup is sum and if it's product, you get something called the tunnel problem, which sort of is like if you have a truck, what's the maximum height of your truck if it's going through a series of tunnels with different heights? If you choose 0, 1 with sup and times, you end up with something probable or probability theory related, which is interesting. So in this case, a weighted graph is actually a Markov process, and the weights represent transition probabilities. And the most likely paths, or algebraic path problem, it finds the most likely sequence of things which can happen. And we already saw this next example with true and false. In the last example, which I won't get into because it's kind of complicated, but you can sort of get more expressive things. So in the case of this power set of the strings of characters. And so epsilon here is just some set of characters, and epsilon star is a strings of characters. And then you can take the power set of those strings, and that becomes a semiring. And the algebraic path problem for that semiring corresponds to the decidable language of a non-deterministic finite automaton. So this is a really computer science flavored version of it. Okay, so why are we talking about matrices in the first place? Well, the idea is that if you take the nth power of a matrix, then the entries of that matrix will correspond to the lengths of the shortest paths, which occur in exactly n steps. So if we choose R equal to our motivating example of positive real numbers, including infinity, and we have an R matrix called M, let's compute its square. So there's this usual formula for matrix multiplication, which gives it square. You take the sum over all intermediate indices of the product going through that index. But in this case, the sum is minimum, and the product is plus, because we're in this sort of bizarro ring, or semi-ring actually. So if you look at this expression and squint a little bit, eventually you'll realize that it's finding the shortest path, which occurs in exactly 2 steps. So K is a vertex. That's some other vertex, maybe the same vertex in your matrix. And Kj represents a path of length 2, which starts in I and ends in J. And the sum of those weights is the length of that path. And when we perform this matrix multiplication, what we're doing is we're taking the minimum of all such lengths. And similarly, hopefully it's not too much of a stretch to understand that if you take the nth power, it's the same thing, except now you have n intermediate indices. So it's the paths of length n that you're minimizing over. And in general, suppose you want to find the minimum path of any length for any number of steps. Well, then you just take the minimum of all n greater than or equal to 0, where m to the 0 is the identity matrix, of all these matrix powers, and you'll end up with the shortest path in any length. And that is the algebraic path problem. So when we generalize this to an arbitrary R, we end up with this really nice expression for the algebraic path problem, which is it's the sum over all n greater than or equal to 0 of m to the n. And the ijth entry of that gives the solution in the algebraic path problem from I to j. So this is a much sort of nicer expression, because as you can imagine, well, first of all, it looks like the geometric series, which is kind of exciting. And then, as you can imagine, the previous expression is actually very hard to use in practice because enumerating those paths can be very difficult. But next, we'll see how this geometric series formula is actually a well-known thing in category theory. It's going to be the expression for the free R-enriched category on M. So we'll talk about that in a moment. Okay, so first of all, let's talk about ordinary free categories. So if you have a graph G, we can think of that graph as a diagram in set. So that diagram is going to have a set of vertices, a set of edges, and source and target maps connecting the edges to the vertices. So if you take this graph and you place it next to each other, so or at least you draw it next to each other. So this graph here and this graph here, maybe a natural category theory instinct is to take the pullback whenever you see a diagram like that. And when you take the pullback, you end up with a graph on the outside of this diagram. So the edges of this graph are the pullback up top, and the source map goes down to the left, and the target map goes down to the right, as shown as in red, if you can see it. So the edges of this graph, I'm going to call it G squared. When you take the pullback, it's going to be the subset of the product which makes the maps commute. And making the maps commute in this case means that the target of the first edge must equal the source of the second edge. So in other words, the edges of this graph are the paths of length 2 in G. Okay, similarly, we can do this in an iterated way where we place the graph next to itself n times, and then we just keep taking pullbacks until there's only one apex at the top. And then the outer edge of this iterated pullback is going to be a graph that you can call G to the n. And similarly, the edges of G to the n are going to be the paths of length n in G. Oh, and sorry, I forgot to ask for questions, so I'll do that now.
There are a couple of questions, but I think they can wait until the end, actually. I don't think they're looking for clarification about anything that's happened so far. Thanks.
Okay, great. Okay, so once you take the n-fold pullback, as I was saying, the edges of that n-fold pullback will be the paths of length n in your graph. And let's say you want to keep track of the paths of any length in your graph. Then what you should do is you should take the co-product over all G to the n for every n greater than or equal to 0. So now this is a graph whose edges are all paths in your graph of length any number. And it turns out that this graph here is the free category on G, which is a well-known construction. So in general, there's an adjunction between graphs and categories. Every category has an underlying graph with edges given by morphisms of that category and objects given by objects, or sorry, vertices given by objects. And the left adjoint to that forgetful functor is what we've been talking about. It's this thing which sends a graph to this infinite coproduct of its graph powers. Okay, so that is the free category construction. And don't worry about the right-hand side of the slide too much right now, because I will explain it more. Sorry, I'm not used to talking this much. But the idea is that, first of all, enrichment, I'll say what that is. And you can enrich in any monoidal category. And when that monoidal category has countable coproducts, which are preserved by the monoidal product, then you get a free enriched category construction, which is given by this adjunction that I've shown here. And the nice semi-rings R that we've been talking about so far will be an example of categories that we can enrich in and do this process. Okay, so are there any questions?
Nope, that's fine.
Okay. All right, so the idea is that an enriched category is like an ordinary category, except for every pair of objects, instead of having a set of morphisms, you have an object of V. So the data of an enriched category or a V category is going to be an object of V, Cxy for every pair of objects X and Y, a V morphism from Cxy times Cyc to Cxc, representing composition. And this is a morphism in the category V. And then also a V morphism from I, which is the monoidal unit of V, to Cxx. And this sort of represents the structure of identities that you have in a category. So it sort of generalizes categories to this case where instead of set C, you have objects of V. And plus there are also lots of axioms, which I have not listed here, but they express basically associativity and unitality for V categories. And I promise we won't need to worry about them. So some of the canonical examples of enriched categories. First of all, a category enriched in set is an ordinary category. A category enriched in the category of categories is a two category. So in this case, between every pair of objects, you have a category of morphisms between them. And then because it's a category, the morphisms in that Hom category become the two morphisms. And in category enriched in abelian groups is a pre-additive category. And I threw this example in because I thought it might be familiar to some people who work on very algebraic themed things. And if you take an algebra class, you'll see this example a lot. Okay, so I've been talking about nice posets a lot so far. And now I'm going to tell you what I mean by that. So we've been talking about semirings, but not posets. So you can actually turn any semiring into a poset using the rule that A is less than or equal to B, if and only if there exists some C such that A plus C is equal to B. So what we're going to do is enrich in these posets. So on this table here, we have an ordinary enriching category D on the left, and then what it corresponds to in our semiring R. So the objects will correspond to elements of our semiring. The morphisms will just be inequalities. So this is a particularly sort of flattened version of enrichment. The coproducts in our category B will correspond to the sum operation of our semiring. The tensor will correspond to the multiplication, and the distributivity of coproducts over tensor corresponds to the natural distributivity that is already an axiom of semirings. So warning, this example that's motivating for this talk is actually super weird. And when you equip it with an ordering, like as I'm described here on the left, it actually gives the reverse of the usual ordering. So 5 in this case is greater than 6, even though in the real world it's less than 6, it's opposite. So quantels are posets nice enough for us. So quantels are going to be the niceness properties of the semiring that we're enriching in. And a quantel is a monoidal closed poset with all coproducts. And don't worry too much about this definition. It's written in a high category theory way, but it won't come up later. But the important part is that it's a poset. And when you do enriched category theory, when you're enriching in a poset, it actually gets a lot easier. It gets weird and counterintuitive in some ways, but it gets easier because all the axioms of enriched categories are now trivial because every diagram in a poset commutes. Okay, so as promised, an enriched category for a quantal R is actually not that bad. So basically, it's just a matrix, and the entries of that matrix will correspond to the Hom objects. So each of those will be an element of R. And the identity and composition structure, because the morphisms are inequalities, they'll just correspond to an inequality on these matrices. So first of all, you want C to be bigger than 1, where 1 is the identity matrix. And that represents the axiom of identities. And you want the square of C to be less than itself. And if you write out the formula for the square, you'll see that that gives the structure of the composition morphism that I mentioned before. Okay, so in general, there's a nice result for enriched categories that if your enriching category B is monoidal closed and it has all coproducts, then you get an adjunction between B enriched graphs and B categories. And this is a super general adjunction, and I think there is a nice construction of it somewhere. But we're really concerned with a special case of this adjunction. So in a special case for a tall R, there's an adjunction between R matrices and R categories. And R category is what's written on the left here. And R matrix is the same thing, except without the additional 2 axioms. And the right adjoint, it's forgetful. It forgets about the 2 axioms. The left adjoint is what we've been talking about. It sends a R matrix to that geometric series formula, sum over all n greater than or equals 0 of the powers of that R matrix. And sort of the big realization is that the left adjoint, this free R category, it's not just the free R category. It also gives solutions to the algebraic path problem. All right, so if you walk away learning one thing from this talk, I hope it's this. This is what I consider to be the big idea that I want to communicate here. And it's basically that if you have an R matrix and you take the free R category on it, then the entries of that matrix are solutions to the algebraic path problem. So I was really excited when I learned this and figured it out. I'm not sure if it's somewhere in the literature. I'm pretty sure it's not. But I think it's a really interesting and useful fact. Because first of all, it lets us use category theory on the algebraic path problem. And it says that it has a certain universal property, right? So being left adjoint means that it has a universal property. And if you can join together R matrices using colimits, which typically sort of glue objects in a category together, and left adjoints preserve colimits, which is one of probably the best theorems in all of category theory, in my opinion. If you can even call it a theorem. But they preserve colimits. So what this does is it allows us to glue solutions together, or at least in theory it allows us. And soon I'll get into exactly where theory meets practice and the difference between the two. But at least in theory, left adjoints preserve colimits, and this can tell us useful things about how to glue together solutions. And that's the end of this section. So I will ask if there are any questions.
Yes, there is a question, which is that is the less than relation on matrices, is it computed per entry?
Yes, thank you for reminding me to say that. It is computed pointwise. So this less than means that one entry ij is less than or equal to the Cij entry. Thank you, that's a great question. Okay, so now we're going to talk about the applications. Okay, so in computer science, there's a big push for compositionality. And the idea is that most real world systems are really huge and complex. And if you want to compute things on them, it'll take a really, really long time unless you have some clever strategy for reducing the time of that computation. So in particular, the algebraic path problem has O of v cubed complexity. So that means that if your graph has v vertices, on the worst case, it will take v cubed amount of time to compute that problem on your graph. And this means that it suffers from combinatorial explosion because as v gets large, v cubed gets even larger. And it's very important to be able to break the algebraic path problem into smaller components, compute it on the smaller components, and then join it together. And actually, that's how lots of algorithms for the shortest path problem and also these generalizations already work, is they break it up in various clever ways. But I'm going to do some theory about it. So before understanding how to break up the algebraic path problem into smaller components, first we need to understand how to break up graphs into smaller components. So for example, we have these two graphs shown above. And what we want to be able to do is glue them together along this vertice, which are closest to each other. And as you can see, that 6 went away and the 0.2 didn't. And I'll explain why that happened in a minute. But first of all, we sort of need a theory to understand this sort of gluing before we can understand gluing the algebraic path problem. So the idea is that what we're going to do is we're going to take these graphs and we're going to designate certain vertices of them as either inputs and outputs. So in particular, if we take the first graph, we can put a set X on the left and a set Y on the right, and give these sort of dashed arrows that I've drawn as pointing to the inputs or outputs of that graph. And then we're going to write that graph using a morphism notation, using G from X to Y, because the input is a set named X and the output is a set named Y. And we can do something similar for the graph, the other graph that we want to glue together. And when we compose them, first of all, we're going to join the vertices, which are mapped to by a common element in Y. And then we're going to decide what weight to put on that vertex. And in this case, that's sort of guided by the math here. So if you formalize this, you can formalize these open graphs as cospans. And you can think of the gluing as taking push-outs over those cospans. And it turns out that push-outs in the category of R matrices, they take the sum over the overlapping data. And in this case, the sum is going to be minimum because we're working in the positive real numbers. So for this vertex, we took the minimum of 9 and 0.2, and we ended up with 0.2. Okay, so that's really quick for how gluing works. Okay, so here's the good news. As I said earlier, left adjoints preserve pushouts. So we end up with this isomorphism. Either on the left, we can glue two matrices together, then take the solutions in our algebraic path problem. Or on the right, we can take the solution of each component individually and then glue them together. But there's a catch to this recipe, which is that the gluing together on the right-hand side is a push out of R categories, not R matrices. So it's not just gluing. When we glue it together, it still has to be a category. And to do that, you have to sort of account for lots of composites that weren't in either component. And taking these push-outs is actually sort of a hard thing to do, and it's sort of complicated. And it turns out that it doesn't really give you useful insight for computation yet. Maybe it gives you useful category theory insight, but it doesn't give you a useful formula. But under certain circumstances, it does give you a useful formula. So it turns out you can define a special sort of open R matrices called functional. And the idea behind functional open R matrices is, I'll tell you about them, but they behave sort of like functions. And then also you can define the black boxing of an open R matrix. And that sort of forgets about the internal workings of an open R matrix and focuses on the relationship between the inputs and outputs. And once you make those two simplifications, you can actually express the algebraic path problem, or the black boxing of it, using just matrix multiplication. So that's what the product on the right-hand side is. You can compute the algebraic path problem between the boundaries on a composite just using matrix multiplication. So I thought that was kind of cool. But I'll explain what I mean by all that. So hopefully I have time. All right, so black boxing, that is what I said earlier. You take an open R matrix and you just forget about everything on the inside and focus on the relationship it induces between the inputs and outputs. So more formally, if you have an open R matrix, G from X to Y, its black boxing is an R matrix from X to Y. So usually we've been talking about R matrices on a fixed set. And the values on this black boxing are going to be the solution of the algebraic path problem starting in X and ending in Y. Yeah, there's no more sections, but are there any questions before I move on?
No, thanks.
Okay, great.
Oh, wait. Yes.
Okay.
So quantiles have two structures, which is the tensor and the join. Are we using the tensor or the join for the enrichment? So I think the question is, what's the monoidal structure that we're using for the enrichment?
It is the tensor. So the join is, it turns out to turn into the coproduct, but the tensor is what we're using for the monoidal product of enrichment. And that's all sort of hidden away in the definition of matrix multiplication over here. So okay. Yeah, so the matrix multiplication uses the tensor, and yeah, that gives a formula over here.
Okay, so there was another question about the push-out diagram. Can you clarify what is the push-out diagram? I think that's probably here. I don't know if the person who asked that question wants to be more specific about which push-out diagram, but why don't you go ahead and explain it?
Okay. Yeah, I'm guessing it's this push-out diagram here. And I don't have my tablet set up, otherwise I would draw it. But the idea is, so each of these open graphs, basically what you do is you turn the sets X and Y into discrete graphs on those sets. And then the dotted arrows become morphisms into the open graph in the center. And so that's how they turn into cospans. And then what you can do is you can place them next to each other because the first one is output Y, the second one has output or input Y. And then you'll end up with a sort of, you'll end up with two maps going into the discrete linear graph on Y. And if you take the push out over those two maps, you'll end up with this graph here that I draw on the right.
Thanks. And there's one more thing, which is on slide 16, there's a question about the sum symbol. So which sum is it? So it seems that it's not the plus of the semiring. So what is that sum symbol?
So yeah, so actually it is the pointwise sum of matrices. So it is the plus of the semiring applied pointwise to these matrices. Yes, so the sum in this talk always represents the sum in the semiring. And because it's written out in terms of entries already, this is just the regular sum in the semiring. If we wanted to not write the entries, then it would be pointwise sum.
Okay, thanks. That's all the clarifying questions at the moment.
Great, thank you. Okay, so here's the black boxing. And it turns out that the matrix product in general, that theorem that I wrote before, it's not true unless we take very special sorts of open matrices. And I hope that this example sort of explains why. So what we can do is we can take the black boxing of each of these open matrices. So the black boxing, the first one, there's a path from 1 to 2 with weight 0.1, and there's no paths from 1 to 3 or 1 to 4. So we end up with a black boxing matrix, which has 0.1 in the first entry and then infinities everywhere else. And also it's the transpose of that matrix, which I use a little transpose symbol because it took up too much space. And then similarly, we can take the black boxing of H. And H has one path from 4 to 5 with weight 0.1, but then there's no paths from either 2 to 5 or 3 to 5. So you end up with a black boxing matrix with infinities in the first 2 entries and 0.1 in the last entry. And if you multiply these 2 matrices together, they don't really line up, and you end up with a 1-by-1 matrix whose only entry is infinity. So if matrix multiplication says that there is no connection between these 2 paths. On the other hand, you can glue them together first. So this picture on the bottom is them glued together. And once you glue them together, a new path emerges. So there's a path from A to B, then B to C, then C to D, and then D to E. And that path has weight 0.4 because, sorry, I'm okay, I promise. Because you add up all the weights which make up the edges of that path. And that gives a path with weight 0.4. So the idea behind functional open matrices is that we are going to explicitly disallow this. So a functional open matrix is going to be an open R matrix, which has no edges going out of its inputs and no edges going, wait, did I get that wrong? Yeah, going into its inputs and no edges going out of its outputs. So the idea is that once you go from one functional open matrix to the next, you can never turn back. So this exact situation can never happen. So here's the theorem that I've written one more time. So the theorem says that if you have functional open matrices, then you can glue them together and take their black boxing, or you can take the black boxing of them individually and multiply those matrices together, and they will equal the same thing. So at least I was happy with this theorem because it took something that was really hard, push-outs of categories, and reduced it to something which is a bit more familiar, which is matrix multiplication. And for more, if you want to read more about this, there are a few papers that you can check out. So mostly the content of this talk is in the paper, the Open Algebraic Path Problem. There's also a paper that I wrote with John Bias and called Open Petri Nets, and it has a lot of the same ideas, but in a completely different context of Petri nets. And then also you can find both of the above and more in my PhD thesis called Composing Behaviors of Networks. So there are some further questions that we can have here. So are functional matrices sort of the tightest condition that we can put on these open R matrices, which still satisfy this equation? I think that there's something a bit more subtle you could probably do. I don't know what that is, but I'm pretty sure that it is not the functional condition. It is sufficient, but not necessary. Another question is there's sort of a relationship between, or at least I mentioned this to a few people, and they've told me that it seems a lot like Van Kampen's theorem. So Van Kampen's theorem is a theorem in algebraic topology, which says that if you have two spaces and you take their union, then you can get the fundamental group of the union using the free products of the fundamental groups of each component. And this is really similar to what's going on here because we're sort of keeping track of paths in spaces, they're graphs, which aren't exactly the same as spaces, but if with a stretch of the imagination can think of them that way. So at least I'm sort of curious if there's any relevant algebraic topology work, or if there's, I have a sense that maybe there's something interesting that algebraic topologists might have to say about this situation. So another question is, if you wanted to enrich in a non-post set, are there any interesting sort of computational examples for that? I'm sure there are. I haven't seen people using free V categories very often, but they are definitely well-known in category theory community. But for example, maybe you could enrich in a graph, in the category of graphs, and that might give something more two-dimensional, like rewrite rules or things like that. And then a last final question is whether or not this can be turned into code. Of course, that's always the question if you want to get funded. But it's also an interesting question here. So not this lemma here, but I've started sort of turning some of these formulas into code. I'm still a beginner at most of these things, but basically I want to sort of try to do some compositionality on the computer. And if you want to talk to me about that, then please feel free to do so. I'd love to chat about it. And that is all I have to say. So thank you very much for listening to my talk.
Well, thank you very much indeed for the talk, Jade.
Yeah, thank you.
Kind of impressive. Okay, well, I'll hand back, I think, to Eugenia to handle what questions are kind of haven't been handled during the talk. Okay.
Thanks. Yes, there's a bunch of questions came in. And I'll try to start in the earlier part of the talk. You may want to share your slides again. So there's a question from early on saying, is there a way to see multigraphs as matrices as well?
It depends on what a multigraph is. I don't know what that is.
Okay, so if perhaps the person who said that, if you'd like to type something more about what you mean by multigraphs, we can come back to that. So there's a question. Yeah, go on.
So I guess because I don't know what it is, I'm unlikely to know the answer.
Okay. So some of the questions that came in early on, you proceeded to answer during your talk. So then the people kind of said, "Oh, you've answered it," and retracted that question. So that's nice. So one person said, "It looks like you might be answering that, but we'll just check." So someone was going to say, can you use a quantile in the place of R, but you confirm that. So then the next question is there a general interpretation for quantiles like there is for Booleans. They said you might be answering that already, but do you have anything else you'd like to add?
General interpretation for quantiles. So I guess the most general interpretation of quantiles is that they are monoidal closed posets with all coproducts. So that's sort of like the really pithy category theory way of saying what they are. But if you wanted to really unpack what that means, it would be sort of summarized in this table on the left. They are semirings with a poset structure such that the poset structure is given by join, or join is the same as coproduct in a poset. And then it has a tensor product, which is monotone, and also that distributes, the plus distributes over in the tensor product. But if you wanted to sort of encapsulate that all really, really succinctly, then monoidal closed poset with all coproducts. I'm not sure if that answers the question, but
well,
that's something.
If the asker would like to say something follow up, they can type some more in there. But there's a follow up, which is, do you see any connections between the shortest sum and the canonical trace calculation in Hagverdi and Scott's UDC categories?
Oh, I haven't read that paper, but that sounds interesting. I think trace is something that sounds very related. I've seen it come up, but I can't say anything specific about that.
So there's the follow-up, the clarifying question about multigraphs, which is, it's interesting because I understand multigraphs can mean many different things, but this question was about graphs where between any two nodes there can be multiple edges.
Oh yeah, so oh, multigraphs, right? So okay. So I guess that what I called ordinary graphs, that is in multigraph in a sense, because this does allow multiple edges between given pairs of nodes. And all this sort of free category and pretty much everything I've done in this talk also applies to ordinary graphs. So, and if you want to see more details on that, it's in my thesis.
Thanks. Okay, so there's a question about finiteness. So in these computations, the algebraic path problem is finitary, as in that it's only paths of length n. In other instances, you might need to sum paths of unbounded lengths. Is there a condition on the semiring R that determines that behavior?
Right, so I guess I haven't thought too much about the case when your graph has an infinite number of nodes. But the adjoint path problem is already sort of an infinite sum. And because we're in a quantile, those infinite sums will always converge, because that's what it means to have all coproducts. But I guess if you are in an infinite graph, then yeah, so even in an infinite graph, all the theory here really only applies to paths of finite length. And you probably need to do something a bit fancier to get paths of infinite length, but yeah, I'm not sure. It's an interesting question, but it's definitely not what's going on here. These are all finite.
Okay, thanks. There's a couple of comments. One is that maybe you don't need quantile lineals, will do fine. And there's another comment for the Van Kampen question. It might help to look for categorizing homotopies of paths.
I feel like I should take notes. These are really interesting comments. Right, so the thing about lineals, yeah, I'm not sure, but I think maybe a lineal might do the trick as well. I'd have to check to make sure I know the difference between a lineal and a quantile. I'm pretty sure a lineal is weaker in some way, but yeah, definitely there's probably a lot you can do even in that generality. It's a very good comment. And then the other comment was it was about thinking about homotopies, right? For the algebraic topology question. Yeah, that's a really interesting idea. I'm not sure what a homotopy would be in this context. But honestly, I think there is probably a nice definition of homotopy here. But I don't have it yet. But yeah, definitely if you want to talk to me more about that, I'd love to. And either of those questions, they're both very interesting to me. So thank you for bringing it up.
Okay, so there's a question saying, is the residual in the quantiles being used at any point in this result? That is the HOM adjoint to the tensor.
It's the residual used. So the monoidal closed aspect of the quantiles, the only way that I can think of it being used is so that products or sum distributes over product. And you need that to get a free category construction. I honestly, I don't know how the internal HOM could be used, but now that I'm thinking about it, I think it might have something to do with subtraction, which would need something very interesting to get involved. Because if you can subtract matrices, then you can write the infinite sum as 1 over 1 minus x. So I'd love to be able to do that in some special case, but I don't know. But yeah, that's also a very interesting question. Thank you.
And there's a question here saying, can you expand? So this is at the bottom of slide 9. Can you expand on the decidable language of an NFA problem? So given the subset construction, does it extend to DFAs?
Oh yeah, so there is some sort of equivalence between NFAs and DFAs. I'm pretty sure there's a way to turn NFAs into DFAs, and that's a nice theorem, which I couldn't remember all the details of immediately. But I guess how this example works is that you'll be thinking about graphs weighted in these subsets. So on each, so you have a set of nodes, and then on each edge, you'll have some set of strings in your alphabet. And the idea is that those are the strings which sort of trigger transitions between the states. And if you want to sort of think about all the possible words that can occur, then you need to sort of compute these matrix powers and think about all possible paths and different sequences of the strings. Sorry, that's a very hand-wavy description, but yeah, that's what I got.
Thanks.
Yep,
I think I have found all the questions. Let's just pause for a moment and see if anyone would like to type in any more questions. And I think that's it. So let's thank Jade again very much. Yay. And thank you all for coming. Do look out for the next talk that we have. Maybe I'll put that slide back up again. And what we're going to do now is have a little bit of social time so that we can just have a little bit of a chat. But Jade's off the hook now, so we won't ask Jade any more math questions. If you want to discuss anything with her at further length, then you could send her an email, but we'll just hang around here in case anyone wants to say hello, introduce yourselves and have a chat. But apart from that, that's the end of the recorded part of this talk. Thanks very much.